All right, let's dive in. Today, we're talking about a hidden rule, a fundamental principle that connects our green energy future, the way we travel to space, and even the deep secrets of the natural world. So, what do a global resource shortage, a rocket, and a spider all have in common? I know, it sounds like the beginning of a really weird joke, right? But these three totally separate things are actually linked by this incredibly powerful underlying rule that really shapes how progress happens. See, the secret here isn't about what these things are, but about the problems they are forced to solve. It's a rule that's all about limits, about scarcity, and that constant, relentless push to get more done with less. And that's the big idea, the optimization principle. It's this concept that real game-changing innovation, whether we're talking about an economy, an engine, or evolution itself, it happens when you're backed into a corner and forced to make incredibly smart trade-offs. And our first example? Well, it's happening all around us right now on a massive scale.
Okay, so first up, let's look at the global economy and specifically one of the biggest shifts we're trying to pull off, the move to electric cars. It's an amazing goal, for sure, but it's slamming headfirst into a really serious resource bottleneck. And when you look at this chart, what's absolutely wild is just the sheer difference here. An electric vehicle needs 4 to 5 times more copper than your standard gas-powered car. And that copper is everywhere. It's in the battery, the motor, all the wiring, not to mention the charging stations we need to build to power the whole thing. And that demand, well, exploding is really the only word for it. Think about this. Back in 2015, the entire EV industry needed about 27,500 tons of copper. By 2025, that number is expected to jump to 1.28 million tons. That is a mind-blowing increase in just a single decade. But here's the kicker. Look what happens next. The projections show that starting around 2026, the world is going to enter a structural deficit. We'll actually be trying to use more copper than we can produce. And by 2030, that gap could be as big as 8 million tons. This isn't just a little shortfall, it's a chasm. So you're probably thinking, why don't we just mine more, right? Well, it's just not that simple. For years, there's been way too little investment in new mines. On top of that, the quality of the copper ore we're finding keeps getting worse. And the biggest hurdle? It takes a decade, sometimes 15 years, to get a new mine from discovery to actually producing copper. You just can't flip a switch. So here it is, our first huge optimization problem. We're stuck with a really tough trade-off. Do we slow down our entire transition to green energy because we just don't have the materials? Or do we pay way, way more for that copper, which in turn makes every EV and every green project more expensive for all of us? There really is no easy answer here. Now, let's completely switch gears. We're going from a problem of global resources to one of pure physics and brutal engineering, the unbelievably hard job of just escaping Earth's gravity. You know, this chart right here says it all. This is the tyranny of the rocket equation in one image. Just look at it. Over 90% of a rocket's entire weight is just fuel. The actual thing you're trying to get to space, the satellite, the astronauts, that's less than 4%. It's kind of like using a giant tanker truck just to deliver a single pizza. For decades, we literally threw rockets away after one use. I mean, can you imagine flying across the ocean and then just ditching the plane? It's nuts. The massive paradigm shift really pioneered by companies like SpaceX was to stop thinking of a rocket as a disposable product and start treating it like a transportation system, a vehicle you can use over and over again. And the results of optimizing for reusability? It's been absolutely staggering. By making the most expensive and complex parts of the rocket reusable, the cost to launch anything into orbit has been slashed by a factor of 5, even up to 20 times. It has completely rewritten the rules for the entire space industry. And this isn't just some idea on a whiteboard. It's a proven fact. With well over 520 successful booster landings and counting, SpaceX has demonstrated that this kind of optimization can solve one of the hardest engineering problems humans have ever tackled. It works, and it works at scale. Okay, for our final example, we're going to go somewhere completely different. We're turning to the greatest engineer of all time, nature itself. And our teacher is an amazing 8-legged architect that's been perfecting optimization for millions of years, the Darwin's bark spider. This tiny creature produces what is, pound for pound, the single toughest biological material known to science. We're talking stronger than steel and tougher than Kevlar. This is not your average spider silk. This is a masterpiece of biological engineering.
And if you want to put a number on it, its main structural silk has a tensile strength of around 1.6 gigapascals. That is just an insane number for something made of protein. But producing a material that incredible comes at a huge cost to the spider. And that brings us right back to the trade-off. See, to make the silk that strong, it's packed with an amino acid called proline. It's the secret ingredient, but it takes a ton of energy for the spider to make. So she can't afford to be wasteful. She optimizes. She goes for quality over quantity, building these huge, sparse, but unbelievably strong webs that can span entire rivers to catch prey. And this is a textbook case of what biologists call evolutionary optimization. It's basically nature's own R&D department running millions of years of trial and error tests to find the absolute most efficient way to survive and pass on your genes when you've only got a limited amount of energy to work with. The spider's web is just a perfect solution to a very old optimization problem. So we've gone from a copper shortage to reusable rockets to a spider's web. What's the thread that really ties all of this together? What's the big lesson from these three very different stories? Well, this table just snaps it all into focus, doesn't it? In the economy, we're forced to balance our climate goals against a very real limit on copper. In engineering, it was the battle to maximize payload while minimizing that overwhelming mass of fuel. And in biology, the spider has to perfectly balance the strength of its web against the sheer energy it costs to build. Every single one is a story of optimization against a constraint. And when you boil it all down, this is the core idea. Real progress isn't just about having more stuff or more power. It's about getting smarter and more elegant with what you already have. The most brilliant solutions, the real breakthroughs, they often come from scarcity, not abundance. It's the constraints that force the genius to emerge. And that leaves us with a final question to think about. As we look at all the huge challenges on the horizon, from sustainable energy to AI to feeding a growing planet, it's worth asking ourselves, where's the bottleneck? Where's the key constraint? And what clever, elegant optimization is going to be the breakthrough that solves it? Thanks for digging into this with me.